Welcome to section number 2 of this course. After we have learned about the fundamentals of GCP, we are now looking closer at TensorFlow and some basics of machine learning. In this section, we will cover the concepts and working knowledge needed to use the TensorFlow framework for high-performance numerical computation workloads. We will then focus on key concepts of machine learning and how to implement them using TensorFlow. So let's start talking about TensorFlow. In this video, we will talk about what TensorFlow is, how the architecture looks like in the current version of TensorFlow 2, and we will introduce the high-level APIs, Keras and Estimator for model training and fitting. So, TensorFlow is an open-source machine learning library which was released by Google that has the goal to meet 3 fundamental requirements of production-ready machine learning frameworks. These requirements are performance, flexibility, and portability. Performance in this context means that the framework is powerful enough to handle very large amounts of data, for example, by leveraging the power of GPUs or distributed training. Flexibility means that we need a framework which is flexible enough to support the latest machine learning research and algorithms. And finally, portability means that the framework should be portable enough to support both parallel predictions at scale on custom applications and prediction carried out on a broad range of devices. So one of the core concepts of TensorFlow is to separate the design of the data workflow from the actual data itself. So the programming paradigm is to first build a data flow graph and then stream data into that graph. Nodes in the graph represent mathematical operations such as summations, sigmoids, etc., where the graph edges represent multi-dimensional data arrays called tensors. If you have worked with NumPy and heard about n-dimensional arrays before, then congratulations, this here is just exactly the same. So why is this programming paradigm designed like this? Well, the core of TensorFlow is written in C++ for the sake of performance and flexibility. However, it's not necessary to program in C++ to leverage these capabilities, because you can, for example, create the graph and streaming from Python without giving up on performance or the ability to do GPU computations. After this basic conception has more or less left been unchanged since the very first release of TensorFlow, a lot of redesign took place with the latest major release of TensorFlow called TensorFlow 2.0. Now, this course will focus on TensorFlow 2, but at the time of this recording, TensorFlow 2 is still in beta, so some minor things might change in the final release. Also, we won't talk much about the differences between TensorFlow 1 and TensorFlow 2, but instead we will learn the concepts of TensorFlow 2 right away. If you're completely new to TensorFlow, then you're lucky, because probably there hasn't been a better time to start jumping on board than now. And a good way to understand TensorFlow 2 is to look at its high-level architecture. Remember that TensorFlow is meant to cater an end-to-end machine learning process from model training to prediction at scale, and this is also reflected by the framework's architecture. Let's quickly walk through this piece by piece. So first, of course, you will need to load in data. You can or you should use the tf.data API for this, which can build high-performance input pipelines. Direct input from in-memory data, for example NumPy, is also supported. When you want to build, train, and validate models, there are 2 high-level APIs that you can use for that. And these are the ones we will be working with in this course. tf.keras is the central high-level API used to build and train models. It's the most user-friendly one. The Keras API makes it easy to get started with TensorFlow because Keras itself provides several model building APIs, such as sequential or functional model, and so you can choose the right level of abstraction for your project. Keras integrates tightly with the rest of TensorFlow, so you can access TensorFlow's more advanced features whenever you want. An alternative to Keras is the Estimator's high-level API. It comes with pre-made estimators such as linear or logistic regression, gradient boosted trees, or random forest, And the Estimator API may not be quite as user-intuitive as the Keras API, but it comes with more flexibility and power. For example, you will need the Estimator API for distributed training. However, the good thing is that you can also export models from Keras to estimators. So in most cases, you can start prototyping your model in Keras and then export it to Estimator if needed for more flexibility. No matter which high-level API you use for your model training, you can choose your distribution strategy freely. For example, for very large machine learning training tasks, the Distribution Strategy API makes it easy to distribute and train models on different hardware configurations without changing the model definition. For example, you can enable training workloads to be distributed on single or multiple machines and include support for CPU, GPU, and even TPU training. After you completed your training, TensorFlow will standardize the output and use an interchangeable format for TensorFlow Serving, TensorFlow Lite, TensorFlow.js, and TensorFlow Hub. So if you want to running predictions in a production environment, you can call the model directly in your application or serve it using one of the basic deployment libraries. And these are the ones right here. You have TensorFlow Serving, a library which allows models to be served over an HTTP REST API. You have TensorFlow Lite, which is TensorFlow's lightweight solution for mobile and embedded devices. You have TensorFlow.js, which enables deploying models in JavaScript environments, such as in a web browser or a server-side through Node.js. And TensorFlow also has support for additional languages, including C, Java, Go, Julia, R, and others. So you're not limited to Python only. This is just the high-level architecture. There are many more components available at low level. But for this course, we will focus on the high-level APIs and see how they integrate with GCP services such as Google AI Platform. So to recap, we have learned about the main requirements for a machine learning framework. We introduced the TensorFlow framework and looked at the main architecture of TensorFlow 2. Also, we discussed briefly the high-level APIs, Keras and Estimator, to train and build ML models, and looked at the different parts of distribution and serving strategies.